Hi everyone, I'm Fa, and now I'm going to talk about the last lab about LCD polarization control. So there are two types of LCC that you know is untwisted and twisted. Twisted you use more like a displacement, and untwisted for polarization control. And in this lab we specifically use untwisted. So I'm going to talk more about untwisted instead. So this is how molecule layout. They lay out parallel to each other when there's no voltage supply, and they go to twist in the plane up into the top when you have applied voltage. So it's going to change the polarizations. So it's going to it's more useful for polarization control. So the way that we calculate the retardance of the LCC is basically a coefficient. This one depends on the thickness in the wavelength and divided by the voltage supply. Then we can convert it into wave by using this formula, and then we can control it to angles. So we can plug into the Miller matrices to calculate the polarizations device. So this one is stroke vectors. It's telling you this one is in a total intensity. This one is a difference between x and y, difference in 45 degrees and 135, and this one is a left or right circular. And from there we can calculate the OP to tell what's the degree of polarizations of the light. So that's the theory behind the lab we will try to do. So let's take a look to the ambiguity of the measurement if we use the exo light. Basically we can take a curve up when we apply the voltage. However, it cannot interpret the difference between above pi and less than pi. So everything it does is wrap it down. Everything above pi will be wrapped down, corresponding to pi, 2 pi, 3 pi over 2, and so forth. So if we need to do the correct measurement, we have to unwrap it. The LCC depends on 5 things: is the voltage supply, the wavelength, and the angle, the incident angle, the temperatures, and it shows polarizations. And I'm going to pass to Greg to talk more about our lab today.
So for parts A through E of the lab, which we were unable to complete, we were supposed to use Axometrics equipment here to basically serve as our linear polarizers with, once again, an untwisted LCC between them. We weren't able to get that to work, but the Axometrics should provide Miller matrix, which basically describes the polarization of the LCC.
And finally, we just want to demonstrate a really good example of using LCC in polarization control. So here we have a linear polarizer at y-axis. This one is the LCC, 45 degrees. This one is a beam splitter, polarized beam splitter, and this one is the detectors. So what we try to do is we try to create a circular polarized come from after the setup, and let's go through here. If you remember, P will pass, and this one will be S will be transmit will back in these directions. So when we change in the voltage applied this, we can control in the polarization here to circular, to elliptical, or linear. So we can control in how much S reflected or how much P transmitted. So we can control. So we can do some polarization control right here.
I'm Greg. So to go over the setup a little bit here, we have 2 linear polarizers crossed at 90 degrees, as we've done in a few other labs. Placed between them, we have an LCC, an untwisted LCC, at 45 degrees, and basically by applying a voltage across the LCC, what we're doing is we're changing the polarization. So we have our Heaney laser coming down the optical rail. And by adjusting the voltage, we were able to get different value from the detector. Here are our results as we change the applied voltage across the LCC. As you can see, the transmittance is higher for lower applied voltages. When we have 0 applied voltage, the molecules are parallel to each other, and as we apply greater voltage, the molecules within the LCC undergo a vertical rotation, which reduces the amount of retardance, and that is what we can see here in our results. This is described in the following equation, where V is the applied voltage. So as you can see, as V increases, we would expect retardance to approach 0. So basically, based on these results, we can conclude that we were successful in setting up an electrically controlled linear retarder. This part of the lab was basically to show that the LCC behaved similarly to a quarter wave plate retarder. We kept the applied voltage constant at 2.2 volts and rotated the LCC. As we've seen in previous labs, we expected to see a sinusoidal pattern. So what may seem out of place here is the presence of multiple peaks over 45-degree rotation, which basically means the period has been shortened. This is the result of using a Heaney laser source. The LCC we've been using was originally designed to operate at a wavelength of about 1500 nanometers, so in the infrared. Given that our source is operating about half that, at 632.8, the LCC behaves more like a eighth wave plate rather than a quarter wave plate.